Hello! Hello, everyone! Welcome to the LIUniverse. I'm Dr. Charles Liu, your host, and as always, please call me Chuck. It is always a pleasure to be working with my co-host, Allen Liu. Hey, Allen, how's it going?
Hi, it's going pretty good.
Okay. Explore any Hilbert spaces lately?
Well, I was doing this thing where I was trying to explain people the idea of why spheres are spiky in higher dimensions, which is becomes even more if you get to a full infinite dimensional Hilbert space.
Yeah, no, I like that. You were talking apples and oranges also with an audience member on our YouTube
Yeah,
channel, right?
right. So
Mhm.
on the comments, I believe for the Chuck GPT episode, perhaps one of the others, we were talking about how um, you can sort of connect the idea of rotation with the idea of a coordinate change.
Mhm, mhm.
So that the question that he was asking was, how does a forward vector know how to interact with an upward vector? And so I was trying to explain the linear algebra of that. That was pretty cool.
Very cool. Longtime listeners and watchers of the universe know that Alan, although he is incredibly well versed in so many different things, actually has formal educational training in pure math.
Yeah.
And this is going to be very, very useful for us, in fact, today, because we have as our guest a theoretical cosmologist. Alan, you ready?
Yeah, I'm ready.
I'm psyched because our guest today is Dr. Katie Mack. Hi, Katie.
Hello. Hi, how are you?
Hey, good, good, good. Thanks so much for being with us today. You have come from a long pedigree, uh, undergraduate at Caltech, PhD at Princeton. You've been in Europe, you've been in Britain, you've been in Australia, you're now in Canada. You are well versed not only in our world, but in our whole universe. So we're really happy to have you here. Can't wait to ask you all kinds of questions. Well, if I'm right, Alan, you got to correct me because I am not a
Yeah.
theoretical, pure mathematician, cosmology person. I'm an evolutionary galaxy observer guy, as you know.
Yeah.
Um, is it not true that our own space time, our universe itself, is actually a Hilbert space?
Well, it's not really because it's a Minkowski space. Because
Ah,
time is the other direction. It's got
that's
the other
true.
sign in the matrix.
Oh
So
man, and and the irony, of course, is that David Hilbert himself actually figured that out right around the same time that Albert Einstein had done it. Like the two of them were pretty coeval in doing the field equations and Einstein and so forth, but Einstein understood them and could explain them. And Hilbert didn't quite have it yet. And so that's why we call them Einstein's field equations, I understand. But that's always so fun to talk about. So many neat things. And Katie, I just wanted to ask you super quick, is there something about space that makes you want to do it? Uh, you know, what is
Um,
it about space?
so I think for me, I know that a lot of my colleagues in astrophysics came to astrophysics because they grew up, watching the stars and learning all the constellations, and they had their telescope in their backyard. Um, and I grew up in LA. The sky was pink. Right? Like
yeah.
we did not see stars.
That
I
light
did
pollution,
I did
man.
join, like, the astronomical LA Astronomical Society at some point, and I went out to the mountains once in a
Mhm.
while. But, like, that was not what drew me into astrophysics. What drew me into astrophysics was really just trying to understand how things work. So I was the kind of person who was, as a tinkerer, like, I would take things apart and put them back together and try and understand how everything
Cool.
fit. And I was always really interested in the physics of everything more than the sort of pretty space picture side. And so when I got into
Ah,
astrophysics, it was because all of the really weird, cool, mind bending questions were
Yeah.
related to stuff that happens in space, like black holes and space time and, the Big Bang. All that stuff was really
ah,
fascinating to me. So I really got into space because that's where you get the most extreme physics.
That makes a lot
I
of
see.
sense. Yeah. A lot of stuff we can't do here on Earth.
Mhm.
I see. Well, that's a perfect segue into today's joyfully cool cosmic thing of the day.
Woohoo.
Did I get the order right this
Got
time?
the order right this time. You've been getting it right more consistently recently.
I do. Thank goodness. Well, it was very cool. It is a recent publication in the Astrophysical Journal, which was really, really interesting to me. You see, as you know, I just said before, I do observational galaxy evolution. And recently, using the JWST, astronomers have found a whole bunch of little tiny dwarf galaxies at redshifts greater than 6. So they are 13 billion years in the past, right? So the universe is less than a billion years old around then. And so there's a lot of unusual things in galaxies then compared to now. And one of the things that found was that dwarf galaxies had an unusually large amount of dark matter inside them in the middle. Modern day galaxies have very little dark matter in the center compared to their luminous matter. But these galaxies had a lot of dark matter. So they're trying to figure out the theoretical background for this. So this research group, led by Anna de Graaf, wound up going to the computer simulations known as Illustris TNG 50. Which actually traces in sort of a virtual universe the real-time evolution from nearly the Big Bang to the present day of galaxies. And they found a bunch of dwarf galaxies and they compared it. And sure enough, they were able to find dwarf galaxies that also in the simulations matched what we saw in real life, and found that these galaxies that were really tiny indeed had mainly dark matter in their centers, as opposed to luminous matter.
It's always nice when the simulations match reality.
Right.
Otherwise, you got to mess with the simulations.
The theory matched the observations, which is like, sometimes you got to do it the other way around. But what was super cool, and Katie, I want you to comment on this, is because they evolved those galaxies forward. In other words, they looked forward in time from those ancient galaxies in the Illustris simulations and found that if you trace them 12, 13 billion years into the future, into what would be our present day universe, those galaxies had normal amounts of dark matter in their centers compared to luminous matter, because they were adding more and more regular matter until they got to reasonable sizes, and then the dark matter was dwarfed by the regular matter. I think that's super cool. Is this exactly what you expect cosmology to do? I mean, this is how galaxies are assembled, right?
So I'm not sure if it's what you expect per se, in the sense that like they had to start with some kind of model of these galaxies and then see what they got from it. The nice thing about this kind of result is that if you can do the simulation of the early galaxy and see something that matches the observation, and then evolve it forward with the kind of physics that we understand, and then you get something that matches today's observation, then it really makes it seem like you're probably on the right track. And that's a nice thing you can do with simulations that you can't do with the universe. Like if you're just looking at distant galaxies, you're looking at galaxies today, you can make some kind of guesses about how things changed over time, or what happened, or is it the same class of galaxies, is it different kinds of galaxies, were they destroyed, did they have mergers, like all these kinds of things. But by using a simulation like that, you can set up the conditions that you see in the early universe, and then let time and gravity happen and see what you get at the end. And if you get what you see now, then you have at least a potential pathway for that evolution that kind of makes sense. And then you have other things you can test. You can test it against intermediate galaxies is somewhere in the middle of that timeline, and see if the numbers line up. And there are various ways you can confirm those kinds of results. But that's what's so powerful about simulations, is that you actually can see what the physics is. Like when they do simulations of the buildup of galaxies from smaller galaxies merging together and creating larger ones, that kind of thing. You can do that simulation. You can see where each of those things came from. Whereas in the real universe, you don't really know for sure.
It's just a snapshot
how that all came about. So so it's a really powerful tool, and especially as simulations get more sophisticated, like this Illustris series of simulations, you can capture more and more of the physics and kind of do experiments, which is a nice thing to be able to do with the universe.
Now, are you using a lot of computational things in your work these days, or is it mostly pen and paper?
It's, I think the what I would call the kind of work I do is sort of semi-analytic. It's not these big, huge numerical simulations like Illustris, where you have massive supercomputers and you get these amazing images of galaxies swirling around. And that doesn't come out of my stuff. Mostly what I do is I set up codes that will basically solve a series of differential equations. So first you write down the equations, and then you feed them to the computer, and you say, solve this
Okay.
stuff over, cosmic time or whatever, and then you see what comes out. And it's, very simplified models, but trying to capture the essential physics, to see, to kind of make projections of what we would observe given certain physical conditions. So it's not as it's not as detailed or as intricate as these huge simulations, but the idea is to kind of take a sort of simple model and see if you can figure out, like, what is the really essential physics that's happening here,
Yeah.
and what are the sort of broad brushstroke things you would expect to see in the sky.
Yeah,
Very
because I
cool.
imagine that with that kind of models, rather than being able to have the granularity of these stars and these galaxies and the dark matter filaments and so forth,
Mhm.
you're trying to tweak the sort of more basic laws of the universe and see whether that matches more broadly what we see in the universe today.
Yeah, so it depends. Yeah, it depends on kind of what question you're trying to answer. But for example, some of the work that I'm doing right now with my group at the Perimeter Institute is we're looking at the possibility of dark matter doing annihilation in the early universe. So dark
Oh,
matter is,
wow.
which we'll talk about later, I think, is some
Yeah.
invisible stuff that's matter, but we can't see it. It doesn't seem to interact with light. But there's a possibility that when dark matter gets into a high density region, some of it can annihilate and create particles that we can see, or particles that do interact with the gas in ways other than gravity.
That's
And
awesome.
in that scenario, the early universe would be full of these clumps of dark matter, where the first galaxies are trying to form inside those clumps of dark matter. And if those dark matter clumps are
Aha.
making a bunch of, high energy radiation and particles, then that can affect how that gas evolves over time. So in our calculations, we're kind of setting up, like, okay, let's say you have a certain amount of dark matter, you have a certain amount of gas. Where does that energy go? How does it interact with the gas? How much does it heat it up or ionize it? What does it do to the spectrum of radiation that's moving through space?
Yeah.
Um, and they're simple models, lots of spheres, stuff like that. But the
The
idea is to
uniform
get
spherical cows. Yeah.
yeah, the idea is to kind of get a feel for what are the physical processes, and what could we expect in terms of, like, how much energy is being dumped into these things, and how could it
Yeah.
change how the galaxies evolve.
When I hear of annihilation, I usually think of antimatter and matter annihilating and creating
Yeah,
energy. Is the
yeah.
idea that dark matter has an anti-dark matter, or that dark matter sort of is anti-dark matter at the same time?
Ooh.
So the idea for the models that we think about, the idea is that maybe the dark matter particle is its own antimatter particle.
All right.
So
Yeah.
so when two
Nice
dark matter
Majorana.
roundabout. It's
particles,
kind
Yeah.
of like neutrinos, maybe.
yeah,
Like
yeah.
maybe
So
neutrinos. Yeah.
maybe neutrinos, yeah. So when two dark matter particles, which are identical, collide, um, if they sort of collide in a careful way, then they might annihilate with each other and produce, pairs of other particles.
That's pretty awesome.
Yeah,
Marvelous.
yeah,
Wow.
That's amazing.
Well, let's go to some questions. I know that we have a lot of them, and of course, they're all the most complicated cosmological things because of the theoretical cosmology guest over here. So, Katie, you ready? Alan, go ahead.
All right. So our first question is going to come from Ellis, who is asking, "What's your opinion on block universe theory?"
okay, yeah. So
Okay,
this,
what is block universe
yeah,
theory? let's
yeah.
For
So
people
let's
this
to
is
start
be
with
an
that.
yeah.
interesting. So it's an interesting kind of way of picturing space time, basically. So a lot of times when we draw pictures of, like, a space time diagram,
Hmm.
what we do is we try and depict. You have space along the x-axis and time along the y-axis, and you can draw like a world line or something moving through space and time through this graph, right? If you imagine that as kind of, you know, let's say now you have two dimensions of space and one dimension of time, that's kind of a cube or something, right? And you can think
Yeah,
of
some sort of
something
prism.
moving through that cube. This is the picture
Yeah.
people have in their heads when they think of a block universe. There's a third
Hmm.
dimension of space. Now it's complicated to picture, but
Yeah.
imagine at first with just two dimensions of space and one of time. Then there's kind of a path. Everything has like a path through that space time, and you can point to a certain spot in that block and say that's now, right? and things
Yeah.
things for later in time are the future, things back in time are the past. But depending on where you are in that block, the past and future is defined differently, right? Like so
Right.
you
Yeah.
can set the past and future for a single point, but some other point is going to have a different past and future. Some other point separated in space, separated in time. For that point, an event is what we call it in space time. Space time for a different space time event. There are different things that are included in the past or the future of that event, and so
Whoa.
there's this weird sense in which, like, let's say that we see a supernova tomorrow that went off in a galaxy, a million light years away.
Yeah.
Then, for us, that's now when that supernova happens. For something several million light years farther away, that's the future. For the thing, for the place where that supernova happened, it's the past, right?
Wow.
So depending on where you are and how you're moving through space and time, past and future are kind of defined differently. And so there's a sense in which you can think of, like, if if everything is already kind of, if in that block, if all of the things are kind of already placed in the block, all of the events are just placed in the block, then we still only perceive the future, or sorry, we only perceive things that are in our past. We catch up to things in the future, but you can kind of picture it as all kind of already, it's already kind of in that
There.
block, right? Yeah, it's already kind of there.
Okay.
That's what the block universe is kind of trying to depict. The idea that the past isn't gone. It's just, it's the future to someone else, right? The future isn't not existing yet. It's the past to someone else.
Okay.
So every point in space and time exists at the same time.
Well, not at the same.
That's the idea behind.
Not at the same time.
Yeah,
Not the same time,
but like, yeah, in some global picture, it all exists on the same footing, right?
Wow.
Okay.
Wow.
And so that's the idea behind the block universe. There are, of course, and it kind of makes sense as well in certain contexts, because there are a lot of things in physics where the equations look the same forward and backward in time. Like, there's no distinction in time, and essentially the only thing that really has a strong arrow of time is thermodynamics. So the second law of thermodynamics says that entropy or decay or disorder increases in the future. And so if you can measure the entropy of a system, it'll be higher in the future, lower in the past. And so in that sense, like, you can tell the difference between the past and the future. But aside from that, it's kind of hard to make those distinctions. And so for a particular observer, there are things that are in the future and things that are in the past. But you could imagine a kind of larger picture of space-time where that's not the case. And then people argue philosophy about what time really means in this context.
Right.
I don't really get into that, but this is what the universe means.
Yeah, well, we could get into it, but go ahead. I mean, what do you think about this block universe now that you've explained it to us so well?
I think it's an interesting way to kind of conceptualize space-time, and it is interesting, to think about, like, like right now, if you look out the window, you do not see a supernova, right? But probably in the next 100 years, there will be one that people will see when they look out the window, and that one will have already happened, right? In some sense, right? So, so
for sure.
it is that the light that will reach us within the next 100 years is already traveling to us from that distant supernova. That light exists. It is moving toward us in space, and so it's so it's very tempting to think, well, that's already happened, but by the same token, when you factor in kind of how you think about relativity and causality, we just have no information about the future, and we can't say anything for certain about the future. And so if there is that light wave traveling to us from that distant supernova, we can't know that. There's a real sense in which the future doesn't exist. That supernova does not exist now for us. It cannot. And
so really, maybe you're thinking that, like, the block has to move. We're not actually a static block. It's like a moving block or something.
Well, it's more that if we really have no information, does it matter if it's real or not? You know?
Yeah.
There's no sense in
Whoa.
protect us if we don't have information about it. And so you can talk about, like, in theory and principle, yeah, there's a light from some future supernova moving toward us already, but that already is defined by something really artificial, which is to take a slice through that block at one time, which you really can't do,
Yeah.
because how that time slice happens depends on how you're moving and where you are and whether you're close to a
Right.
gravitational field. And so the only
Yeah.
thing you
Those all
can
change the
really,
angle of the
like, yeah, and so the only thing you can really rigorously define is your future light cone, like the
Yeah.
the part of the universe that will come to you in the future, the part of the universe that has come to you in the past. And so
Mhm.
it's there's a sense in which you can't say that something is happening now or in the past until you actually observe it, and then
Yeah,
it doesn't
yeah.
matter what you talked about it before.
That that is so mind blowing. I love that, and especially relevant because, as you said, you published this book about the end of the universe,
Mm.
which is now, in this context of our conversation of the block theory, actually relevant, because what you're
Well,
saying is that the end
relevant
of the
anyway, I
universe.
say.
Well, it's relevant anyway. Yeah, it's true. But the idea is that the end of the universe doesn't yet exist, is what you're
Right.
basically saying. We
Yeah.
should not think of it as already existing within this huge block of space and time, but we got to wait for it to show up, and that's
Yeah, I
kind
mean,
of important.
we really can't say anything about it. I do have a diagram of the block universe in my book because it's a useful
Ooh,
concept to talk about.
okay.
But there's also, like, I don't think that it means that there's sort of predetermination, which I guess is kind of the
Mm,
way that the block universe is kind of built up.
fair.
Yeah,
Yeah.
yeah. So what does it mean? I mean, visually speaking, do your if you view the end of the universe now, right,
Mm.
Well,
from our mind's eye, what are
yeah.
we seeing? What do we see? This sort of heat death, utter darkness, complete nothingness, or are we just waiting for the membranes to snap back and hit each other again so that we can have a new Big Bang?
I mean, I don't know which way the universe is going to go in the future. I can't say. I do have kind of pictures in my mind of what the different endings look like,
Mm,
but that's not the same as knowing which one it'll be.
Yeah,
But that kind of I don't know, depiction of space time that you use in the block universe, that is part of how I visualize, like, the future,
hmm,
in
okay.
cosmology. So
right.
it's a useful thing to have in my head, I guess.
Right. No, that's cool. Mentioned the membranes bouncing because that's part of an idea that if you
Mhm.
are working in string theory or in multiple dimensions beyond that, that's the idea of the cyclical universe, which I know that you had some knowledge about based on what you had done in the past in your research thesis with Paul Steinhardt and stuff like that.
Yeah, so that's called the ekpyrotic model of the universe. That's kind of an
Aha.
older version of it. So when I was working on my thesis, my PhD advisor Paul Steinhardt was with his colleagues developing this idea of a cyclical universe that involved higher dimensional membranes called branes, kind of
Hmm.
colliding. Um, I wasn't working on it. I was working on other things related to dark matter and the early universe, but
Mm.
I heard a lot about it at the time. Since then, that model has been kind of updated and revised, and now it doesn't
Aha.
involve these higher dimensional spaces.
Oh.
There are these sort of fields, scalar fields and stuff. So it's a
Okay.
different kind of
Yeah.
model now, but it still is a cyclic model of the universe where you have an ending and then a new beginning, or cycles of existence
Yeah.
in the cosmos, which is an interesting possibility of that there would be some new universe that comes out after ours. But
Well, that's been part of religions forever, right? I
mhm,
mean, I was this is my own ancient history. 20 years ago, just
mhm,
walking around giving a tour of the Rose Center of Earth and Space at the American Museum of Natural History, where I was working, and we had talked about the aging of the universe, and some kindly old man started speaking to me in Chinese
mm,
because he got the sense that I speak Chinese, and he was like explaining to me that actually this. Big Bang thing is flawed. According to Buddhist teachings, the universe goes in these cycles of
Mm.
billions and trillions of years, and things always get reborn. And I was like, oh, that's very interesting. Thank you. I couldn't really say you're wrong because I didn't want to
Mhm.
say that because I don't know,
Mhm.
but I also didn't want to say you're right because those kinds of ideas are not scientific. They may be right, but they're non-scientific, right? But you have to deal with that too in your at some point. I imagine that you're thinking about the end of the universe from a scientific point of view inevitably
Mhm.
goes to the stuff that is not scientific, right, which is valid and meaningful but not scientific. I mean,
It's very interesting. I've since I wrote my book about the end of the universe, I've gotten lots and lots of messages from people who have read it,
mhm,
and lots of those messages are have shared with me how their religious uh, beliefs connect to the
mhm,
ideas in my book. And
mm,
the fascinating thing is that it's a lot of different religions, but
Yeah.
they all find some connection. To like they'll say, oh, this thing that you talked about, that's what my book says. This thing that you talked about, that's what my book says. And so it's fascinating how people find these connections and patterns, from connecting their spiritual beliefs to ideas that are coming up in science. um,
yeah.
the idea of the cyclic universe, though, I think is one of the kind of interesting distinctions between a lot of the cyclic cosmologies of some of these religious ideas, versus the ones that people are proposing in cosmology,
Hmm.
is that in the theological ones, there's usually some kind of sense in which the next cycle is better, or you learn
Oh,
something from the previous cycle, or it's like
uh-huh.
improvement upon, or something like
Hmm.
that. That
Hmm.
doesn't There's nothing that says that that has to happen in cosmology. And I'm just
Fair.
like, there's not
Yeah.
necessarily anything particularly interesting that comes through a an end of universe to a new universe in these cyclic models.
Hmm. Yeah.
Sometimes there's some sense in which the entropy, the low entropy of the early universe can be set up by the previous cycle, but it's not like better. you know
Yeah. It's not like
Mhm.
better or worse
Not like a
specifically. It's just
redemption,
another one.
in the way that it might be in theology. But it's also really
I
interesting to
see.
me that much of the response that I've gotten from people, religious or not,
Hmm.
when they hear about ideas about the end of the universe, is a lot of people say that they really like the idea of a cyclic universe because they want something to come again, come
Happen
after.
afterwards.
They
Hmm.
want there
Yeah.
to be something that outlives our universe or that follows our universe, so it's not just existence is over,
Mm.
Yeah.
which I find really interesting because even if our existence, if everything in our universe is completely destroyed, I think a lot of people want there to be something else that carries
Yeah,
on,
it's
even if
true.
there's no
I wonder.
memory of us, which is kind of
Yeah.
fascinating.
It sort of feels like it's like a reflection of our personal level, right? Like
Mhm.
we also want to, leave behind our legacy or be confident in the
Yeah.
future of humanity, right? Like if
Absolutely.
our personal existence ends well before the universe does, we
Hmm.
still want there to be something beyond us. So I
Right.
imagine we just want that for our universe as well.
Yeah, and I think and that's one of the things I kind of talk about a little bit in the book, which is that when people think about, man, this is getting a little bit dark, but when people think about their own death,
Hmm.
a lot
Yeah.
of times when people come to terms with that, because it's inevitable, we're all going to die.
Hmm.
When people
Yeah.
find ways to come to terms with that, a lot of those, sometimes sometimes people think of it in terms of like, well, there's going to be an afterlife and I'll be happy and that's okay. But a lot of times, even if you don't believe in that, people think, well, at least I've left behind something useful about, my great
Right, a
works, or
legacy.
my,
Hmm.
the impact I've had on the world, or my children, or the books that I've written, or, even just in small ways, I've affected the world, and in the future it'll be different because I was here.
Yeah.
And if you follow through the idea of, the universe will end, then
Hmm.
there
Yeah.
will be a time when nothing that we've done will have mattered, right? Like all of our existence will be erased. There will be no
Wow.
legacy at all for any of us in any way, not just
Wow.
humanity, but like the universe, right?
Hmm.
If the
Hmm.
universe is really going to end. There's a slight caveat of that in a cyclic model sometimes, where
Yeah.
sometimes a little bit of information can come through, but it's usually like information like the the state of a scalar field or the position of supermassive black holes. It's not like our books, right?
I see.
um,
Yeah.
and so
That.
so I think it's really, while writing this book, it made me think a lot about what it means, like how can there be meaning in life that
Mm,
doesn't rely on some future justification, like, oh, it'll all turn out okay in the end, or we'll all
yeah.
get our just rewards, or our legacy is what's important. You kind of have to find a way to find meaning in the universe in the moment that doesn't rely
Mm.
on the future, because at some
That
point that
makes
future is
so
not
much
going to
sense.
exist.
Yeah, I like that. I mean, yes, I guess, as an astronomer and an observer who knows, has watched stars die, right, and knows that our planet will die and galaxies, our Milky Way will die as it crashes to Andromeda and all those kinds of deaths start making me feel very philosophical about the end of life. And it's really okay. We know it's going to happen. I mean, I don't want it to happen anytime soon because I have so much more I want to do, and I'm very excited
Sure.
about that.
Yeah.
Yeah.
But when you say that death is dark, it's only if it is in a way that is permanently dark, actually with no light, right? Even when stars die, their remnants go on, and then they can sometimes trigger things like supernova explosions, or their material gets scattered off to go make new planets. So this whole life death cyclical stuff happens all the time on the short scale. Heck, even in The Lion King, right? The circle of life.
Yeah.
You got that
I love how
happening.
the short scale is like several billion years as far as you're concerned.
Yeah, I imagine so. Anyway, that's really cool, and it really does get into theology, doesn't it? I mean, that's something
Yeah.
you know a lot about. You, tell us a little bit about,
If you
comment a little bit about that. I mean, the
what you like.
connections. Yeah, as much as you'd like to say.
I mean, mostly I'm just talking about like what I already said, that there
Mhm.
are
Yeah.
there are a lot of different ways that people kind of think about the universe that are connected to their personal beliefs, and I think that
Yeah.
there's just a kind of, I think there's a basic desire in humans to understand the bigger picture, to
Yeah.
find
Mm,
context and meaning and something important and beyond themselves. And I think that for a lot of people, religion is that thing that they think of.
Yeah.
They think of the divine, and they want to connect with the divine, or they want to understand the divine, and
mm,
that's the thing that is bigger than themselves, that will bring meaning or purpose, or something, some deeper sense to the universe. um, and that's, I think, that fulfills a deep need that a lot of people have. um,
mhm,
the way that people approach religion versus the way that people approach science is very different, right?
mm,
And so it's they're different methods, they're different ways of going about looking at the world. And so I think
Yeah.
it's hard to make any direct comparisons, because the way that science is done is it's a kind of very distributed, um, long-term project where
mm.
there are a lot of controls in place to try to deal with human biases, and there's a kind
Yeah.
of iterative process of constant evolution, in a
Yeah.
way that is less common in religion. But
Mhm.
Yeah.
and that the standards for data and evidence are very different.
Yeah.
Yeah.
And
I,
but
I've
I think that they I don't think you can kind of draw very direct connections between the two ideas, or ways of looking at the universe, because they do work in such very, very different ways.
yeah.
Yeah.
I think ideally, at least in my mind, they're meant to do different things, right? Like you're saying, in science, we want to take out our biases. We want to see what the universe is doing and find all that there. Whereas from what I understand of faith systems, it's the human element is very important. It's like very central to everything. It's like all about what we think and things like that. Not always. It depends on different from faith to faith. But
Yeah, I think the commonality, though, is that in science, we do talk about finding objective truth, but I think in the day-to-day sense, what we're doing is we're creating a model of the universe, some kind of
Yeah.
mathematical model of what's happening, and that model is always going to be imprecise, and there's always going to
Yeah.
be stuff that's missing from that model, and we're
For
constantly
sure.
trying to refine it, and we hope that it gets closer to, you know, ultimate reality, whatever that means.
Mhm.
But
Yeah.
we are kind of building a picture, you know, a model or a cartoon picture of the universe,
Yeah.
and you know, that's also, people use religion to create a model of how the universe works as well. But
Right.
the point is that the methods for creating those models are very different, and the
Yeah.
Mhm.
standards by which those models are judged and evaluated and you know, refined, those are very different.
Very
Makes
cool.
sense.
Hi, everyone. Turns out we had so much to talk about with Dr. Katie Mack that we've got another episode of it coming. So, thank you for listening to part one of this Universe conversation. Please join us for part two with Dr. Katie Mack, which should be out in just a couple weeks. If you like what you see and hear, please support us on Patreon. And as always, thank you for being a part of the universe.